And I've broken up the slides into two parts. Okay, so let me show you the slides. If you look at the slides, I have 75 slides, 76 including the title slide. The first 40 slides is part one, and there's an exam on just part one, which is a 50-question exam. And on the part two, we have I believe, a 25-question exam. So you have two exams on this chapter. Okay. All right. So in my other class, I was not able to finish part one, and we probably won't be able to do that today. Okay. So what we're going to study is medical applications of pressure. Yep. So when you walk into a doctor's office, what is the first thing they do? They measure your blood pressure. Okay. So pressure is a good indicator of health or ill health. Okay. So we'll look at medical applications of pressure. Okay. Here's a quote by Da Vinci: "The noblest pleasure is the joy of understanding." Okay. When you understand something, it feels good. Okay. So we'll look at this table. The table lists typical values for fluid pressures in the human body. Okay. All pressures are quoted are gauge pressures. What does that mean? All pressures are gauge pressures. So P is the absolute pressure, actual pressure. P minus atmospheric pressure is gauge pressure. Okay, and that is gauge pressure. And the reason it's named that is because most gauges, that's what they measure. They don't measure the actual pressure. They measure the actual pressure minus the atmospheric pressure. So when you go and measure your pressure in your tires at a gas station, that's a gauge pressure. Okay. So 32 psi that you have in your tires, the 2 atmospheres is, the actual pressure in your tires is 3 atmospheres. 2 minus 1 is 3 minus 1 is 2 atmospheres that you measure. Okay, so here are some numbers that are familiar to you. So these are arterial blood pressures. These are in millimeters of mercury. And in a healthy adult, the systolic pressure is about 120, and the diastolic pressure is about 80 millimeters of mercury. And here are various pressures in the veins. In the venules, it's 8 to 15 millimeters of mercury. In veins, it's about 5 millimeters of mercury. Okay. Look at this. In an infant, the systolic pressure is about 70. That's quite a bit less than for in an adult. The diastolic pressure is about 40. Okay, why is that?
Less area to cover?
Yes, less area to cover. You don't have to push the blood as far. Okay. All right. So, so here are some of the pressures that are shown. Oops. Okay, so here, see. So there's the 120 millimeters of mercury in the arteries and 85 millimeters just before it starts branching off. And the capillaries on the arterial end, it's 35 millimeters. Okay, and again, fluid flows from high blood pressure to low blood pressure. In the venule ends of the capillaries, it's 15 millimeters of mercury. Okay. And look at this. From going from here to the heart, there at the, it's 4 millimeters of mercury. Okay. Now this pressure drop is from 120 millimeters to 85. That's a 35 millimeter drop. Okay. Here's this vein from here, 15 to 4 millimeter drop. That's a 10 millimeter drop. All right, so let's talk about one very interesting thing. The flow rate in a pipe. Here's the high pressure, low pressure is given by pressure difference. That's how you make a fluid flow. And again, you've seen this formula before, you don't have to remember it. So we're just going to point out something interesting. R is the radius of the tube, of the blood vessel. 8 eta is the viscosity of the fluid, L is the length of the fluid. All right, so let's answer this question. Let's say, again, I'm just making up these numbers. 5 liters of blood are flowing out of the heart per minute. 5 liters per minute. How much blood is flowing into the heart? If 5 liters of blood are flowing out of the heart per minute, how much blood is flowing into the heart? 5 liters, okay? The same amount. Okay, look at this. So here's the problem. This pressure difference is 35 millimeters. That is 35 millimeters. This pressure difference, 15 to 5, is 10 millimeters. That is 10 millimeters. So here the pressure difference is 3.5 times this guy. So how do you have the same flow rate here than here? Did you guys understand the problem? Okay, so the way that's achieved is you just make this blood vessel thicker, R thicker, wider. Since the pressure drop is smaller, this blood vessel is wider than that guy. Okay? And so now we can figure out how much wider it is just from these numbers. So that's the neat thing about these formulas. You look at this diagram, you're given the pressure difference, and now I'll tell you exactly how much wider this tube is compared to that. Okay? So this pressure was 3.5 times higher than this pressure difference. So this number for this guy has to be 3.5 times higher than this guy. Okay? So you just have to figure out 3.5 to the power 1/4. And you can do this in your calculator. So, and you can try this on your calculator. 3.5 to the power 0.25. And that's 1.37. Equal to 1.37. So what that means is, if the radius of this guy is R, the radius of this guy is 1.37 R. Okay, so the vein that is bringing the blood back to the heart is 40% wider. Yeah. So again, just from these numbers, you can figure that out, okay? All right, so that's what this is showing. Here's a graph that shows you the pressure variation. So if you measure the pressure here, the highest pressure here is the systolic pressure, which is 120 millimeters of mercury, and the low pressure is about 80 millimeters of mercury. Okay, again, these are average values, okay? So that's what this table is listing, okay? It lists the pressure in the veins and so on, okay? We'll come to these numbers, the pressure in your bladders and stuff like that. That is the cerebrospinal fluid, and we'll talk about that as well. And this is the ocular pressure that when you go to an ophthalmologist, that's what they measure. And the ocular pressure is 12 to 24 millimeters of mercury. Okay? And All right, so the cardiovascular system consists of two pumps. Okay. Here are the two pumps, the ventricles. Again, so this is the left ventricle and this is the right ventricle. Okay. So let me show you a number again. So the right ventricle, what does the right ventricle do? It sends deoxygenated blood to the lungs. So here it sends the blood to the lungs. Okay? And when this pump compresses, when this pump contracts, see, it builds up a pressure of 25 millimeters of mercury. This guy, the left ventricle, has got to send the blood to the entire body. When this guy contracts, he creates a pressure of 120 millimeters of mercury. Okay, this blood only has to go a short distance. So you can, so right now, so right away you can tell you have two pumps. This guy is working much harder. Okay. So you actually have four pumps, but these are the two main pumps. The atria are also pumps. Okay, but they're sort of collection chambers, and they just send the blood to the ventricles. Also, you can see all the valves in your body are one-way valves. Blood flows in one direction, okay, and you can see that from the shape of the valve. Okay, when you increase the pressure here, what you end up doing is you close the valve and the blood goes to the lungs. Okay. So all the valves are one-way valves. Okay, so the cardiovascular system consists of two pumps, no, really four pumps, and a complex arrangement of vessels that transport blood through nearly every part of the body. So the purpose of any pump is to create pressure in a fluid, okay, by exerting a force directly on the fluid. So if you take a balloon and squeeze it, and you'll increase the pressure in the air. Okay? So the left side of the heart pumps blood through the rest of the circulatory system, returning it to the right side of the heart. All right, I'm going to show you some little app that we'll learn about this in the second half of this chapter. Okay, so, but we'll. Where is it? I'm looking for a diffusion app. Okay. All right, so we want to learn about diffusion. Okay? So imagine the following. So let's say this is oxygen, and these are carbon dioxide molecules. Okay? So blood brings oxygen to the cells, and oxygen has to diffuse. It actually diffuses into the interstitial fluids. Okay? And carbon dioxide has to diffuse to the blood vessel, okay, to be transported back. All right, so let's remove the divider. So carbon dioxide is a higher concentration, oxygen is a higher concentration here, okay? and molecules from a higher concentration will move towards lower concentration, and molecules from a higher concentration here will move towards there. Okay? Okay, so what's happening? Carbon dioxide is being transported into the blood vessel. Oxygen is being transported to the cells. Okay. Very slow process. Okay, so if you breathe in air in your lungs and you want to give oxygen to your legs, you can't rely on this process. That's why you have the circulatory system. The blood absorbs the oxygen and transports it there. Okay. So if you're more than a few cell large, if you're a single cellular object, then you rely on diffusion. So this is ultimately how stuff is exchanged. Okay? But that can happen only over a short distance. So if you have to transport stuff over a larger distance, you have to have a circulatory system that takes nutrients and oxygen the major distance, and then the last mile is via diffusion. Did you guys understand that? Okay. All right, so you saw that. So we'll mention a couple more things. Okay, so molecules from higher concentration move to lower concentration, and they did on their own because of random motion. Okay. Now, what if you want to move? So, what if you want to move stuff from? So let's say there are a few red molecules here, and you want to move it in this direction against a concentration gradient. When does this happen? So for instance, if your digestive system has nutrients and the blood already has higher concentration of nutrients, and you still don't want to waste all those nutrients, you want to absorb that. Or in your kidneys, when you have toxins already in the kidneys, and you want to move more toxin out of the blood into the kidneys, so against concentration gradient, if you want to move some substance, that's called dialysis. How do you do that? If you guys understand what I'm saying? So you increase pressure here and you can move substance. Okay? So by higher pressure, you can move stuff against concentration gradient, okay? Against toxins or nutrients and stuff like that. When water moves from a higher gradient to a lower gradient, that's called osmosis, okay? All right, so we'll learn those three terms: diffusion, osmosis, and dialysis. These are motion of molecules, but all this happens over only very short distances. Okay? So if you want to be big and large, you have to have a circulatory system to carry stuff over large distances. Okay? All right. So again, we'll talk about all of this. I'm just sort of giving you a preview. Okay? So again, what are the two main pumps? The left ventricle and the right ventricle. Which is the stronger pump? I'm sorry? The left ventricle, okay? You see this guy creates only about 25 millimeters of mercury. This guy creates 5 times the pressure. And so we'll see how that is related to the structure. Okay, so we'll come to that. All right. Heart valves are open or closed by pressure. Okay. Pressure differences across them. In addition, the valves between atria and ventricle are aided in opening by cords attached to them. Okay, so these atria are sort of reservoirs. Blood collects there, deoxygenated blood collects there from the body, and the atria pump the blood into the ventricles. Okay, and you see these valves are one-way valves, and they're aided by cords there attached, and they open wide, and the ventricles will fill up. And when the ventricles contract, these valves close, and the blood goes to the lungs. Okay? Okay, so blood is nearly incompressible. So when the ventricles pump, so when these guys compress, okay, blood out of the heart, the aorta balloons to taking up the extra volume. So when this compresses, these blood vessels, the aorta expand. Okay. Okay, so again, here is the left ventricle pumps blood, oxygenated blood through the entire body. And once the oxygen is depleted through the capillaries, uh, the blood is brought back to the heart, which sends the blood, the right ventricle sends the blood to the lungs, where oxygen is picked up again and then comes back to the left atria. And then you start the cycle again, atria to ventricle and to the entire body. Okay, so that's the circulatory system. Okay. So here shown is a graph of the pressure inside the atrium, inside the aorta. Okay, so inside the aorta, here's the pressure, and this pressure is a function of time. So here is the systolic pressure, and there's diastolic pressure, and you see one cycle is about 1 second, so you have about 70 heartbeats a second. Okay. I mean, 70 heartbeats, 60 heartbeats a minute. Okay, shown is the graph of the blood. Again, the diastolic pressure, this minimum pressure, is due to the elasticity of the arteries. Okay, so when the blood vessels are like rubber tubes, and when they compress, that's the pressure. Okay, so the heart is not doing any work. That's due to the elasticity of the blood vessels. So here, blood pressure in various parts of the body. Again, like I said, the flow rate is given by the pressure difference and times the radius of the blood vessel to the power 4. And in the denominator is eta is the viscosity and L is the length of the tube. Okay. Again, we've learned that we can control flow rate to various organs in the body. Okay. And so, for instance, you guys remember when you, after a meal, to your digestive system, the flow rate can increase by as much as 5 times. Okay? And that's mostly done by vasodilation. Okay? So you increase the radius of the blood vessel. Okay. So again, here are the blood pressures in various parts. Okay. Resistance in the system can cause pressure to drop. So as the blood flows around the system. So again, flow rate is pressure difference divided by the resistance. Okay? And resistance is given by this formula for laminar flow. Okay, so we saw that there's only a small pressure drop in the venous system from the capillaries back to the heart. There's only a small pressure drop, 10 millimeters. Okay. This is because 2 major veins returning blood to the right side of the heart are each larger, so these guys are larger than the aorta. And we saw they're 37% larger than the aorta. Okay. All right, so you saw that in your so blood comes through the aorta, then it branches into small branches. Blood is supplied, nutrients and oxygen are supplied, and then the depleted blood is brought back to the heart. Okay. All right. Many of the blood's duties are performed in capillaries. Okay. So again, all the exchange happens, all the exchange of oxygen and nutrients happens at the capillaries. Okay. Including the removal of waste products and the transport of nutrients and oxygen to the cells. Capillaries are about 10 micrometer in diameter. Okay, so the diameter of a capillary is about 10 micrometer. Okay. Now, the size of an atom is 10 to the minus 10 meters. Okay, that's the size of an atom. And a micrometer is 10 to the minus 6. So the width of a capillary is roughly the size of 100,000 atoms. Okay? So that's the size of a capillary. The process, so here are the three words: the process of diffusion, osmosis, and dialysis, and active transport are in action through the capillary walls. Okay, so again, diffusion is a motion of molecules from higher concentration to lower concentration. Okay, it happens naturally. Osmosis is the motion of water from higher concentration to lower concentration. Dialysis is motion of substances other than water from lower concentration to higher concentration. Okay? And active transport, so when you go from lower to higher concentration, the molecules don't want to do it on their own. You might have to spend energy to do that, and that is active transport. Okay, so again, this is motion of molecules with or against concentration gradients. Okay, and sometimes you have to spend energy, sometimes you use pressure to do that, and so on. Okay, so we'll talk about all of that. So, an incoming arteriole branches into capillaries. Okay, some of which have sphincter muscles. So these guys have sphincter muscles to control flow. So they can control flow by either closing the sphincter muscle or relaxing it. Okay, so you can control flow of blood to specific organs. Okay, okay, so here's another point. Okay, so you don't have sphincter muscles in big arteries because you don't want to stop blood flow to the entire body. You have sphincter muscles at smaller blood vessels, so you can control flow to specific organs. Okay. Okay. So some of the arterioles have sphincter muscles to control flow. So another important method of flow control is constriction and dilation of arterioles. Okay. Now here's an important point. Most capillaries are 100 times longer than their diameter, so that's the diameter of a capillary. Okay. A capillary is typically 1 millimeter long. So 1 millimeter is that much. Okay, you can barely see that. That's how long the capillaries are. Okay? And in a second you'll learn each capillary is sort of supplying roughly to 100 cells. It's servicing about 100 cells. Okay? So let's look at that. Now here's another important point. Velocity of the blood in the major arteries is about 30 centimeters per second. Here, blood is flowing at 30 centimeters a second. 30 centimeters is 1 foot. So the blood is flowing this fast. Okay. If the blood flows this fast, would you be able to exchange any of that stuff that you saw via diffusion? That's too fast. You got to slow down the blood when they come to the cell. Okay. And you see, in the capillaries, they're moving about 0.03 centimeters per second. That is 0.3 millimeters per second. So this divided by 1,000 is that. So the blood from here to here has slowed down by a factor of 1,000. Okay, you had to slow it down. Now, at that speed, you can exchange stuff. Yeah. The question is, how do you slow it down? All right, so this formula tells you the flow rate is the area of cross section. Okay, area of cross-section times the speed at which the fluid is flowing, okay? So that's the flow rate. Okay, let's say again, we'll come back to this. 5 liters a minute are flowing out of the heart. How many liters are flowing across the capillaries? 5 liters, okay? So you see, if you want to, the flow rate has to be the same. So if you want to reduce the velocity, you have to increase the area. Okay, so the area of this guy and the area of cross-sections of all the capillaries added together, that's 1,000 times greater. That's how you slow down the blood by a factor of 1,000. Okay, did you guys understand that? Okay. All right, so most changes in average blood velocity, other than those produced by the heart speeds up the blood by doing work. I mean, it's like pushing the blood, okay, are due to changes in total area of cross-section. Okay, so you change the area of cross-section by having more and more blood vessels, and you slow down the blood. Okay, so smaller cross-sectional. Okay. It's necessary to have low blood velocity in the capillaries and to have many capillaries to have effective exchange of substance between blood and the interstitial region by diffusion and related slow processes. Okay, so ultimately the cells get all their nutrients and stuff via diffusion. Okay, and diffusion is a slow process, so you have to slow down blood for that to happen effectively. Okay. The human body has 10 billion capillaries, giving a capillary every few cells on the average. Okay, so we have about 1 trillion cells, okay, in the human body, and 10 billion capillaries. So 100 cells per capillary. Okay, so roughly 100 cells are being serviced by each capillary. And how big is a capillary? It's a millimeter long. Okay. Now here's another very interesting fact. So do you guys know the radius of the Earth? Anybody know the radius of the Earth? It's 4,000 miles. Okay. And so if you go around the Earth, that's 2 pi r, 6 times, that's about 24,000 miles to go around the Earth. Okay, so how many capillaries do we have? 10 billion. Each capillary is a millimeter long, which is 10 minus 3 meters. So 10 to the power 7 meters, that's 10,000 kilometers. That's about 6,000 miles. So if you put all your capillaries together, you can go around the Earth a quarter of the time, 1/4 the distance around the Earth. So that's how much your capillaries will add up. Your capillaries will add up to 6,000 miles. Okay. Has anybody seen the body exhibit? Do you guys know what I'm?
I've seen pictures, yeah.
Okay. No. Have you seen pictures? Okay. Orlando had it a couple of years ago. So they have some kind of process where they can I'm looking for the one where they have just the blood vessels.
Is it in the smaller category?
I'm sorry?
Is it in the smaller category?
Where?
Like it's in the side panels where there's like 4 set options.
Oh, yeah.
Those smaller. Yeah, it was on the right.
Okay. I don't see blood vessels.
There's more.
All right, there's
It's
circulatory.
right there.
Mm-hmm. Vascular system, okay. There you go. See, there's the blood vessels in the lungs. It was pretty amazing. In the legs and all that. But again, 6,000 miles of capillaries. Okay. All right. Now here's another problem. Okay. So let's go back to this diagram. All right. See the blood pressure here. Okay. So this was wider, and the blood pressure here. So this number again. This just gives you a feel for it. So the pressure is lower here, and the pressure difference is not too high. Okay, so if you, with that pressure difference, if you want to bring blood from your legs to your heart, that pressure difference is not good enough. So how do you do that? How does the body solve that problem? Okay, that's a long distance that's quite a bit of height to cover. Here's how the body solves that. Okay. Your skeletal muscles also help in the blood flow back. Okay, so you see when the skeletal muscles contract, they squeeze on the blood vessel inside them, and these blood vessels, these veins, have valves, one-way valves again. So when the skeletal muscles contract, they force blood up towards the heart. Okay, so anytime you have large veins in between muscles, the muscles are aiding the pumping of the blood back to the heart. Okay? So that's what's happening. The return of blood to the heart through the veins is aided by the contraction of skeletal muscles, especially in the extremities. Okay, because the pressure difference is not good and is large enough to pump it all that height. Okay? When muscles contract, they bulge and force blood out of the larger veins, as shown. The one-way valves, so your body is full of one-way valves, the cardiovascular system. Okay? So when these guys squeeze, this valve closes and that valve opens. Okay? The valve towards the heart. People are rarely completely relaxed. Even when sitting quietly, small motions such as shifting in a seat or tensing aid circulation with this muscle pump. Okay. In people that are completely motionless, so in the military they train you to be that. Why do they do that in the military? Because it'll save your life. If you're hiding from the enemy in the bushes, you don't want to move. Yeah? All right. In people that are completely motionless, such as soldiers at attention, the return of blood to the heart is slow enough that they may faint. Okay. Yeah.
So like when we sleep, is that why our blood pressure drops because we're not actively moving? Because I can't imagine we're constantly moving in our sleep.
Well, when you're sleeping, you need your energy requirements are lower, so you don't have to pump blood as much. You are a very well optimized machine. You do not waste energy under any circumstances.
But then just the heart pumps it up.
Yeah. So you guys have seen all these soldiers standing at the Arlington Cemetery and stuff like that, and so that can happen. Yeah. So anyway, you have several pumps. Your skeletal muscles also help pump the blood back. Okay. So here's another point. And this works for wide pipes. Okay, so big, large blood vessels. Okay. At the bottom, you saw that if here's a fluid of height h. At this point, the pressure is rho. Rho is the density of the fluid. G is the gravity, acceleration due to gravity times height. Okay. So the blood pressure at the heart is that. Okay. The systolic pressure is 120 millimeters of mercury. And at the bottom, at your feet, the pressure will be the heart pressure plus rho GH, okay, in big blood vessels. And at the head, it's rho GH minus this, okay? So the pressure at the heart minus that. Okay, now here's a problem. So let's say if your heart is weak, this pressure is low, and the pressure at the heart at the head would be small because this height doesn't change, and then you're not pumping enough blood through your brains, and you can faint. Okay, so if pressure in major arteries in the head drops too low, the person can potentially faint. Okay. In the circulatory system, it's convenient to measure the depth or height of the fluid relative to the heart. The pressure drop due to resistance is negligible in major arteries. In wide tubes, the pressure drop due to resistance is negligible. For a standing person, the pressure in the major arteries increases below the heart and decreases above the heart by this amount. Okay? So you have to worry about that. Okay. Flow regulation. Again, like we've seen, there are times when you want to regulate blood flow to various parts of the body. In the winter, what do? You cut off blood supplies to your skin so you don't lose too much heat. After a meal, you send more blood to your digestive system. Okay, so I'm sort of. So here's a great illustration of this. I'm sort of addicted to playing chess online. And after a meal, I tend to lose more games because so, all right, so the body has considerable latitude in blood flow regulation. Blood flow to individual organs and total blood flow through the body can be varied. So that's what you were talking about when you were sleeping. Your blood pressure is lower, and you're not circulating the blood as fast through the entire body. Okay? Blood flow is adjusted by both changes in vessel radii and by changes in blood pressure. We've talked about this. Again, blood flow rate is high pressure minus low pressure, pi r square. R is the radius of the blood vessel, 8 eta L. Okay, so if you're a good athlete, you don't rely on pressure changes as much. What you do is you rely on dilation more. Why is that? When you're a good athlete, you don't want to make your heart work harder. Okay? So anyway, that's the conditioning. So recall, okay. So again, flow rate is pressure difference divided by resistance. Okay, so it's not, the body adjusts blood flow by changing vessel radii. Most vessel dilation and constriction take place in the small arteries and arterioles in the smaller blood vessels. Okay, I want to show you. Okay, also here's another thing that we take advantage of. So drugs can also induce vasodilation or vasoconstriction. Okay. So, for example, a local anesthetic may be administered with a vasoconstrictor. So when you're administering a local anesthetic, you can also put a constrictor in it, vasoconstrictor, to reduce blood flow to that region and prolong the time that the anesthetic remains in place. Okay, so if you want the anesthetic's effect to be there longer, then all you do is add vasoconstrictor to the medication and restrict blood flow there. Athletic conditioning makes vasodilation more effective, and blood pressure increases need not be as great. Okay, so thereby they increase their stamina as well. Okay, during strenuous exercise, blood flow may quadruple. So if you're running, let's say, and the blood flow to your muscles can increase by as much as 4 times, with a 50% increase in arterial blood pressure and significant vasodilation by a factor of 27%. Okay, here's another important point. Flow is adjusted by changes in arterial blood pressure, while venous blood pressure remains constant. Okay, so what we are saying is you increase flow rate. When you're changing blood pressure, you're changing blood pressure at the arterial end. Okay, so you're changing blood pressure here. Okay, the venous system, the blood pressure remains the same. That's constant, and you're aiding the flow back by using other pumps. So that's what we're saying there. All right. So high blood pressure can, of course, be dangerous. It can rupture vessel walls, perhaps causing a stroke or heart attack. The heart must exert a force to create high blood pressure and is strained. Okay, so you don't want to rely on high blood pressure. Okay, high blood pressure often occurs with aging. Okay, and may be designed to maintain flow in vessel narrowed by plaque. Okay, so here's another evolutionary thing. So I keep writing this formula, but okay, so as you age, plaque gets deposited and your blood vessels narrow. This becomes smaller. So to maintain flow rate, you have to have a higher blood pressure. Okay, so that's an evolutionary thing too. Okay, so now this is unavoidable narrowing. Okay, and that is arteriosclerosis. Okay, now here's another point. So Q, the flow rate is pressure difference divided by resistance. Resistance is given by this formula, 8 eta L by pi r to the power 4. Okay, so this formula doesn't exactly apply to our blood. That's what we're saying here, but it's good enough. Okay, so Poiseuille's law is only valid for non-turbulent flow, a high blood. Okay, Poiseuille's law is widely applied to blood flow and does give a good qualitative description. So it's not accurate, but it's good enough. Okay, so we just want to mention that. Turbulence, diagnostic indicator. Okay, so let's see. We don't have a diagram here. Okay, so you guys remember, so here's a blood vessel. This is when fluid flows smoothly, this is called laminar flow. And if blood flows in turbulently, what happens is with turbulent flow, the resistance goes up for turbulent flow. And if resistance goes up, then to maintain flow rate, you have to work harder. You have to have a higher pressure. Okay? So with turbulent flow, resistance goes up, and so you want to avoid that. But oftentimes we use this to as an indicator. Turbulence can be detected by the sound it makes. Okay, so if blood is flowing like this in your blood vessel, it's not noisy. When blood is flowing like that in your blood vessels, it's noisy. When you hear the water flowing in your kitchen, that's what's happening. Okay, anytime you hear water anywhere in your house, that's turbulent flow. Okay, so for example, a noise that a water faucet makes is the sound of turbulent flow around its valves. Turbulence in the heart, major arteries, and veins is easily detected by a stethoscope. I guess. So when they use the stethoscope, normal heart sounds are caused mostly by valves closing. Flow through a leaky valve is turbulent. Okay, since a partially closed valve forms an irregular obstruction. Sounds made by leaky heart valves are called heart murmurs. Okay? So when you hear the term heart murmur, that's what's happening. Somebody has a leaky valve. Okay? A hole between heart chambers is another cause for turbulent flow. Such a hole exists in newborn infants and normally closes within a few hours after birth, sometimes before birth. If you have an aneurysm, okay, an aneurysm is the ballooning of, and that causes turbulent flow as well, okay? Aneurysms are quite dangerous. If one bursts, stroke, heart failure, or severe hemorrhaging is the result and often fatal. So turbulence is used to make common blood pressure measurements. Okay, you saw that the blood pressure measurement is made by what you do is the cuff applies pressure and it collapses the blood vessel by applying pressure. You make the blood vessel collapse, and as you're releasing pressure, the blood vessel opens up. Okay. And when blood flow first starts, that's turbulent flow. And that's what you're hearing by placing a stethoscope here. That's what you're listening to, the first flow of blood. And that happens at the systolic pressure. Okay? So turbulence is used to make common blood. Systolic pressure is measured by noting the cuff pressure when flow first resumes. Okay, and the pressure in the cuff, as the pressure in the cuff is lowered. The first flow is turbulent. The cuff pressure is reduced until there is flow during all parts of the cycle, and all sound goes away when the flow is completely laminar. Okay. Okay, now we're going to answer the following question. You guys know that the capillaries are very thin, right? And the blood aorta is quite thick. Okay. So let me show you the numbers again. Okay. So you see the pressure in the aorta is 120 millimeters. In the capillaries, it hasn't dropped much. It's 35 millimeters of mercury. So the question we're going to answer is the following. You guys have blown up a balloon and have it burst, right? If you have a thin balloon and the air is at high pressure, it'll burst. Okay, so the question we want to answer is the capillaries have thin walls and the pressure is quite high. Why aren't they bursting? Okay, so that's the question we want to answer. All right. So Mr. Laplace explained this. His law tells you the following. Okay, so the tension, okay, the surface tension is given by the pressure times R, the radius of the tube. Okay, so this tells you the strength of the walls. Now the capillary walls are not very strong, and the pressure is quite high. So the reason they can get away with weak walls is they're tiny. The radius is very small. So even though the pressure is high, the radius is very small, and so they don't need to be that strong. Okay, and that's what. Okay, so the higher pressure, the thicker the wall must be. But small diameter tubes such as capillaries have thinner walls that might be expected. Okay, and they can get away with being weaker just because they're very tiny. Okay. So the answer is that the capillaries have small diameters and therefore there is less area for pressure to act upon, and hence the force on the capillary walls are smaller. Okay. All right, that'll also explain the following. Okay, so we'll come to that in a second. It can be shown that the tension in the wall is given by P times R. So a tiny capillary wall with thin walls tolerates pressure as large as the fourth of those in the aorta. The capillary radius is so small that tension in the walls is also small. Because this is so small, the tension can be small, and you can get away with a weak capillary wall. All right, now we want to answer this question. All right, so you saw that this is a pump and that's a pump. Which one is the stronger pump? The left ventricle. You see it's creating a pressure of 120 millimeters of mercury. So how do they create different pressures? What's that? Okay, yeah, thickness of the walls and the size of the ventricles. Okay, so here we go. Okay, so here's that formula again. Here's the left ventricle. The walls are thicker, okay? And the left ventricle is also smaller. So the pressure is gamma, the tension in the walls, divided by the radius of the pipe. Okay, so divided by the radius. So the left ventricle, remember, has to create pressure of 120 millimeters of mercury. The right ventricle creates a pressure of 25 millimeters of mercury. 25 versus 125. This pressure is 5 times greater. Okay, so a 5 times greater pressure is created by this being bigger, walls being thicker, and also the size, the radius of the pipe being smaller. Okay, so a smaller ventricle. So these two factors combine to give you a pressure 5 times greater. Okay, in congestive heart failure, what happens? The heart gets larger, this becomes larger, the pressure drops. And for you to have the same pressure now, you'd have to have the heart muscles work harder. You have to make gamma harder, larger, okay? So in congestive heart failure, your heart is working harder, okay? So like this, an enlarged heart in congestive heart failure must exert a larger force on its wall to create sufficient blood pressure, damaging it further, okay? In a normal heart, the walls of the left ventricle are thicker and the ventricle is smaller in radius than the right ventricle, as shown. Okay. So the left ventricle creates pressure 5 times greater than the right ventricle. Okay. All right, so here's, so let's do this. I'll push this. Why did it stop? Friction. Okay. So if I want to keep it moving, now I have to keep pushing. Okay. Friction in the fluid stops the blood. Okay. So you have to keep pumping it. Okay. So the heart is doing work. Okay. The rate at which you do work is power. Okay. So the heart is spending energy. Okay. So here's the kinetic power, the amount of work the heart does per second to get the blood moving. Okay. So the kinetic power to get the blood moving is, this is the velocity, this is the kinetic energy of the blood per unit volume times the flow rate. That's how much energy the heart is spending per second. Okay. Pressure power, so when the heart contracts, it's increasing pressure on the heart. Okay. And so that's like lifting an object. That's potential energy. Okay. So this is how much energy it's spending to increase the pressure. Pressure times flow rate. Okay. The heart does, okay, so here's another point. So this guy slowed down. What happened to that energy? Okay, so it had, this object had energy in the motion, and now it doesn't. What happened to all that energy?
It's expended.
I'm sorry? I'm sorry? It got converted to thermal energy, okay? Ultimately, everything gets converted to heat energy, okay? So, and that's why you have to get rid of the heat from your body. How much do you have to get rid of heat from your body? You guys are all like a 100-watt bulb. You have to get rid of 100 joules of energy per second, remember? Okay. The heart does work and expends energy. Ultimately, all the energy that the heart expends ends up as thermal energy. Okay. The heart gives energy to the blood in three forms. Blood is given kinetic energy as it's accelerated out of the body in the circular. It also supplies gravitational potential energy. Okay, so when the blood is lifted to your brains, it's gravitational potential energy. And another form of potential energy is supplied to the blood when the heart increases blood pressure. Okay, this potential energy provided is negligible. The heart provides negligible potential energy, so we'll ignore that. So most of the energy spent is in speeding up the blood and increasing the pressure. Okay, so those are the two. Okay, so there is the kinetic energy per unit volume times flow rate, pressure times flow rate. Okay, so here's how much energy it's spending. Okay, so to speed up blood when you're resting, not exercising, so when you're active, it's 0.15 watts. And then you go for a run, the kinetic energy, it increases by a factor of 100. Okay. Pressure power, this is 1.5 watts, so most of the energy is spent in increasing the pressure. Okay. And that's the total power of the heart when you're resting. Okay, here's another interesting fact. While resting, the power output of the left ventricle is not large. It's about 1.65 watts. But it must supply this power continuously for your entire life. It cannot rest. Okay. In addition, the heart rests about 2/3 of the time. Okay, so it's pumping and then rests twice that time and then pumps again. Okay. So the actual power output of the ventricle during contraction is about 5 watts. Okay. All right, so that's the power. Okay, now we'll come to the bladder. Okay, when the bladder is empty, the pressure inside is 0 when the bladder is empty. When the bladder fills up, the pressure is 25 millimeters of mercury. Okay, so, and when the bladder reaches its normal capacity, the normal capacity is about 500 cc. Okay, excuse me there. Hello there. Can you hold up your drink? So that's the bladder capacity. Okay. Well, more, yeah, regular soda can. That's 400 cc. Okay. The micturation's reflex, okay, the reflex to P is triggered by a bladder pressure about 25 millimeters of mercury. So when your bladder fills up, then you send a signal to the brain. Okay. The micturation reflex triggers muscle contraction around the bladder. So bladder fills up, the reflex makes your bladder contract, and the pressure rises to 110 millimeters of mercury. Okay. Accentuating the sensation, so that so the sensation is accentuated, and you want to go to the bathroom. You know? Pregnant women experience increased bladder pressure due to the weight of the fetus resting in the bladder. The capacity of their bladder is also less than the normal 500 cc because the space the fetus occupies. Okay, so the bladder pressure when urinating is normally 30 millimeters of mercury. So once urine starts flowing, the pressure difference is about 30 millimeters of mercury. Okay. Now, let's say in men, let's say if the prostate presses down on the urinary tract and narrows it, then you have to maintain a higher pressure difference. Okay. So for bladder pressure is about 30 millimeters of mercury, but any obstruction of the urinary tract, such as from a swollen prostate gland can necessitate pressures as large as 70 millimeters of mercury. Okay, so you would have to have almost twice the pressure difference. Okay. Okay, so now we'll briefly talk about the cerebrospinal fluid. Okay. There's the cerebrospinal fluid. Okay. So here's what it does. Okay. That fluid is produced in the skull. Okay, here's the job of this. So the cerebrospinal fluid supports the weight of the brain with a buoyant force. So your brain is floating in this cerebrospinal fluid. Okay. Now, if your brain sat on this table, the table is pushing back upon it, and that force is damaging. Okay. So it's floating in a fluid. Okay. So this is supporting the weight of the brain with the buoyant force, acts as a protective cushion. Okay, so let's say I go and hit my head against the wall. Okay, my brain didn't hit my skull because of the protective fluid. Okay, if I hit my wall and if I didn't have the cerebrospinal fluid, I would have a bad headache. Yeah. And it also supplies nutrient filtered from the blood. Okay. So there are three main functions. All right. Is generated in the skull. It's produced in the skull and circulates around the brain through cavities in the brain and called ventricles and down the central canal of the spinal fluid. Okay, so it's generated in the skull. It provides a protective layer, nutrients, and shock absorption. And this fluid goes down the spinal cord. Okay. All right, so now, so it goes down the spinal cord through this little duct. If the duct gets blocked, then you have problems. Okay? And that's a narrow duct. So if you get blocked, now you keep producing the fluid and the pressure will increase in your skull. And increased pressure is not good. And this happens to infants. Okay? So in infants, this can easily get blocked. Okay? So the cerebral aqueduct is narrow, 15 millimeters long. 15 millimeters is about that much. Yep. That connects the third ventricle to the fourth ventricle of the aqueduct. Stenosis and narrowing of the cerebral aqueduct obstructs the flow of CSF and has been associated with hydrocephalus. Yeah. Such narrowing can be congenital, so when you're born, arise via tumor compression or through cyclical gliosis. Yeah. When continued production of CSF, with continued production of CSF, an obstructed aqueduct leads to pressure buildup in the brain. Yeah. And that can be bad news. Okay. Pressure in the cerebrospinal fluid is measured using a spinal tap. Okay, when you measure, you're using a spinal tap to measure the pressure in this fluid. Unfortunately, this method does not detect hydrocephalus. So if you have a blockage there, measuring the pressure here, you can't detect blockage because the difference is not high. Okay. It's not convenient to measure pressure in the brain directly because of its bony structure. You can't measure the pressure of the fluid directly there. Okay. 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 The skull and the spinal column contain about 125 cc of cerebrospinal fluid. 125 cc is about this much. Okay, so that's how much cerebrospinal fluid you have. Yep. And that's it's providing three great functions. It's providing buoyancy, it's providing nutrition, and it's providing shock absorption. Okay? So when you do a spinal tap, you create a hole and fluid might leak out. Fluid will leak out. So how do you prevent that? You don't have a whole lot to lose. Okay? So the skull and the spinal column contain only about 125 cc of CSF, so even a small loss is significant. Loss of CSF deprives the brain of some of its buoyant force support and of its protection from physical blows, so headaches are a result. You know. So CSF is slowly replenished over a period of 4 or 5 days. So for 4 or 5 days, you don't want to don't want a leakage. You had a spinal tap, right? Yeah. And in the meantime, lying down distributes the remaining cerebrospinal fluid evenly. Okay. Okay. Spinal taps are performed for many reasons: to administer anesthetics, to introduce dye for contrast on an X-ray, and to withdraw CSF for density measurements, among other things. Yeah. So if you're healthy enough. Okay. All right, B will stop here. Okay.